Namaste. Okay, guys. Again, the year's winding down. We're in the spirit of kind of keeping it easy. All right, as easy as we possibly can. I'm gonna try and do a light version of what's known as electric circuits, circuit analysis, and what's called Ohm's law. Okay. Um, what a circuit is a way that we use is our basic technology for using the electroweak force. Okay, and every circuit has three parts to it. All right, and just so you can see the symbology. All right, you have two lines like this, and that represents what's called a voltage. Okay, and then you have this. These would represent like your wires, and then you have kind of a jagged line like that, and that represents something called a resistance. R. Okay, a voltage is the concept behind it is sometimes called electromotive force. Basically, it's a battery. It could be a battery or a generator. It's the thing that makes a current of electrons go through a conductor, like a wire. Okay, and it's measured in something called a volt. Okay, and the more voltage you have, the more the electrons want to get from the positive end or from the negative end to the positive. So the short line tends to be the negative, the long line tends to be the positive end of like a battery. So let's just use a battery analogy for now. So if there's 1 volt of what's called potential difference, but let's not get into that too much, but if the battery is 1 volt, then the electrons only want to get through the circuit to this end so bad. If it's 10 volts, they want to get from the negative end to the positive end 10 times as much, okay? And that's how voltage works. So obviously, something that's 10,000 volts, the electrons want to get from here to here really quickly, all right? And we'll start to go through, things that they wouldn't normally go through, all right? Like your skin or something like that, which is why you never touch something that's like 10,000 volts, because normally your skin is a bit of a resistor, right? So like for low voltages, electricity doesn't go through it. That's why you could pick up like a 12-volt car battery by the poles like that, and nothing's going to happen to you. Okay, but you'd notice if you like ever touch the two prongs on your if you ever accidentally touch like two prongs in a wall outlet as you're like plugging something in or taking a plug out, and you ever made contact like that, you might have gotten a decent shock. Why? Because that's not 12 volts, that's 120 volts. So the electrons wanted to get from one end to the other so bad that they actually did go through your skin and your body. Okay, and by the way, your skin tends to be a resistor, but the inside of your body is not. Your inside of your body is mainly liquid water, 80%, filled with charged particles called ions. Okay, so you're on the inside, you're a very good conductor. But anyway, so what happens is the electrons go from one end, okay, through the resistor, okay, and then back to the other end. And what's a resistor? Well, a resistor is anything that drains power from the electrons and kind of stops them a little bit. Okay, so it could be one of those ceramic resistors that you find in the electronic components of electronic devices, or it could be a refrigerator. It could be your hair dryer. It could be your toaster oven. It could be a microwave. These days, it could be the massive battery pack inside an electric vehicle. Okay, so that's what a resistor is. And there's a relationship that relates voltage, resistance, and the part that you can see, and I forgot that part, the part that you can't see is the current. Okay, and that has the variable capital I, if you could say it, yeah. And current is measured in something called an ampere, often just called an amp. Okay, just so you know, 1 amp, what it is, 1 ampere of current is the equivalent of 1 coulomb of charge moving through a section of wire in 1 second. Okay, so it's actually a rate. it's a coulomb per second moving through a conductor. 2 amperes would be 2 coulombs of electrical charges through a section of conductor in a second, and so on. Okay, and again, just so you know, because like a coulomb of charge is large, 1 ampere of current is a large current. 1 ampere of current going through your body is more than enough to stop your heart, fry your brain, things like that. It's deadly to you. That's why oftentimes we'll use, instead of amps, we'll use milliamps, just like with coulombs, or we'll use microamps or things like that, okay, of current, micro. Okay, now there's a relationship between voltage and current and resistance that goes like this. V is equal to I times R, okay? And this is called Ohm's law. And that's what governs resistance, or that's what governs the activity inside of a circuit, okay? And if you notice, if I rearrange this, I is equal to V over R, okay? This is why you have to have some resistance in a circuit, because as this number gets smaller, because it's an inverse relationship, if this number gets smaller, this number gets bigger, okay? So if R, for example, all right, goes to 0, this current goes to infinity. Now, will it really go to infinity? No. But as this gets smaller, suffice to say, this gets larger. This is why what's called a short circuit is really, really bad. All right, so in the wiring in your house or something like that, if there's no resistance in the circuits like in your house, like say some mice got into your walls or something like that, and they chewed through the insulation on the wires, you know, that are inside your walls or something, and the pieces of metal inside those wires make contact. If that happens, the resistance goes way down and way down fast. And what does that mean? The resistance goes way down, and the current in that circuit goes way up. And this is why this is bad. Because current, you can look at current as if it's, all right, like current, the current of a river or something like that. Okay, it's analogous. It's not quite the same. It's a flow of charges, but unlike, like, let's say you had water going through a pipe. The pipe is hollow. The water doesn't touch anything, all right, as it's going through the pipe, except the sides of the pipe. Inside an electric wire, like a copper wire, there's a whole bunch of atoms inside. I mean, that's what the copper wire is made of. It's made up of copper atoms, okay? And those copper atoms have electrons on them. And so the free electrons that are inside the conductor start to move, and you get a current, but it's not like water where a molecule of water would just go straight. An electron in an electric current bumps into these other electrons in the copper atoms as it's moving. So it generally goes in one direction. So it might hit an electron here, and then hit an electron here, and then hit here, all right, and then maybe go straight for a while. It might even bounce back a bit, okay, and then go forward and things like that. But it generally goes in, one direction when you average it all over time. Okay, well, the problem is, and this is the thing with electricity, every time there's an impact, there's a momentum exchange. And that makes these electrons in these copper atoms move. Well, movement is heat. And if we were to take physics too, we'd learn a bit of thermodynamics. What is heat? It's the movement of molecules and atoms. The faster they move, the hotter they are. The slower they move, the colder they are. Okay? So when these electrons start bumping into the atoms inside the conductor, the more they do it, the hotter that conductor actually gets, okay? So if you have a little bit of current, that's one thing. But if you have a ton of electrons, the more current you have going through, the more collisions, the more random collisions you have with the atoms in the conductor, and the hotter that conductor gets. It's something called ohmic heating, okay? Now, this is the reason why, if you've ever looked inside if you ever seen like your toaster oven or something, it's got those heating elements inside there, these thin wires that are coiled. And what you do is you put a caca load of current through those thin wires, and they start to get so hot that they glow and they radiate heat, and you can cook with them. Okay, that's you might have seen it if you have an electric heater or something somewhere in your house. The glowing coils, that's what's going on there. Now those coils are designed to take that heat without failing. Though, when this happens inside the wall of your house because some small animal chewed the insulation, it's not designed for that, and it could start to melt the insulator around the wire, which is usually some sort of plastic, and it could ignite it, and then you got a fire inside your wall, and then your house burns down, and that's really bad. Okay, so anyway, so that's the concept of Ohm's law. Okay, all right, so Ohm's law is V is equal to I times R. Okay, all right, so anyway, here's one more thing with this. All right, resistances, by the way, add. Okay, which is something that you have to know. All right, so there are different ways to hook up resistors. So if I have a resistor right here, and I'm going to say that's like a 3 ohm resistor. Now the symbol is the Greek letter capital omega for ohm. That's their letter O. Okay, and let's say that I hook it up in line with a 2 ohm resistor. Okay, this is physically the exact same thing. The two resistances add to the electric current going through this section of a circuit. This is physically the same exact thing as having 1 5 ohm resistor in the way. Okay, the electric current doesn't know the difference between a 3 and a 2 hooked together like this in 1 5 ohm. It's physically the exact same situation. When you have resistors hooked up in such a way that the current has to go, the current I has to go through both of them, it has no choice but to go through both of them, we say that they are hooked up in series. Okay? Now, and when resistors are hooked up in series, they add. So we'll call this R1, call this R2. So the total resistance of resistors in series is the sum, that's that summation symbol, like net force, so it means you add. It's the sum of the resistors, okay? Ri to the n, or whatever the notation you use, but it means add 1 plus 2, and if there's a third one, add that, and so on. Now another way to hook up resistors is we say the word is in parallel. So that goes like this. So let's say I have some current and it's moving through a conductor, and then I have a branch here. Okay, it branches off. Now this point right here has a special name. It's called a junction point. Okay, and what that means is that the electrons can go this way, or some can go this way. Okay, so what's going to happen is, let's say I have one resistor right here, and I'm going to make that a 4 ohm resistor, and I'm going to have another resistor right here, and I'm going to make that an 8 ohm resistor. All right, and then I'm going to have the current rejoin over here. All right, so what's going to happen is some of the current's going to go through the 4 ohm, some of the current's going to go through the 8 ohm. Now the reality is more of the current is going to go through the 4 ohm. Why? Because that's less resistance. Okay, and the current goes through the path of least resistance, at least more of it does. Some is going to go through the 8 ohm, but not as much is going to go through this branch as through this branch. And it's through the resistors that we control the flow of electricity. And that's why there are electrical engineers who spend 4 years getting a bachelor's degree studying this. Okay, so that's what happens there. So the thing about resistors in parallel, okay, we'll call this R1 and I'll call this R2. Resistors in parallel, the way they add is called a reciprocal relationship, and it looks like this. 1 over the total resistance is 1 over R1 plus 1 over R2, plus if I had a third resistor, 1 over R, to the n, whatever, however many resistors I have hooked up in parallel. Okay, so there you have that. Okay, so what is the total resistance in this case? All right, let me lower this a little bit. All right, so if I hook the 4 and the 8, what's the total resistance in this section of the circuit? Well, I have 1 over the total resistance is equal to 1 over 4 ohms plus 1 over 8 ohms, okay? All right, which is, okay, 0.25 plus 1 over 8 is like 0.12, and if I get it wrong, just put it in the comments or something like that. But it's like half of that. It's like 0.125 or something like that, okay? All right, so 0.125 plus 0.25 is 0.375. Tracking on that? Okay, hold on. I left my calculator on the desk. Okay, so 0.375, I know you're getting a little bit of a glare there. Okay, sorry about that. Okay, so let me go up here. So I have that 1 over R total is 0.375. Okay, but that's not my total resistance. Remember, this is it's a reciprocal, so what I'm going to do is I'm going to take the reciprocal of both sides. All right, and R total is equal to, sorry, I got to get around that section of the board. My son, when he was younger, tried to erase the chalkboard with some sandpaper, and that's why that's there. Okay, is 1 over 0.375, which is, okay, 1 divided by 0.375 equals 2.6 repeated thereabouts, so it's I'm going to round it off to 2.7 ohms. Okay, now notice I hooked up a 4 ohm resistor and an 8 ohm resistor in parallel, and the total resistance I'm getting from them is 2.7 ohms total, all right, in this section. So to the current going through here, the current doesn't know that it's branching off and going through a 4 and through an 8. To the current, this is exactly the same situation as if you replace this 4 and 8 in parallel with one 2.7 ohm resistor straight through. Okay, it looks the same way. And something to note about that, when you hook up resistors in parallel, the total resistance is always going to be less, okay, than the resistance of your lowest resistor. My lowest resistor is 4, my higher one is 8, okay? So, and notice that my total resistance is 2.7. Tracking on that? Okay, so that's the deal with that. All right, so that's some basic circuit analysis. All right, now what I'm going to do is this. I'm going to show you a typical Ohm's law problem. I know this video is going to be a little bit longer, but just kind of bear with it. And I apologize. We're kind of fitting this in at the end of the year, but we're almost done. So let's say, I'm just going to think numbers off the top of my head. So I have let's say I have a 10 volt power source, and then I have a 3 ohm resistor, and then I have a 6 ohm resistor, and then I have a 2 ohm resistor, and then that's the circuit. Okay, so what I want to know is how much current is going through that circuit. Okay, so what I'm going to do is I'm going to use Ohm's law. V is equal to I times R. Okay, so V I got, that's 10. I is what I'm looking for. So the question is, what's the R? Well, the R is the total resistance, okay, in the circuit. Well, what is that? Well, they're in series, so my total resistance is going to be 3 plus 6, which is 9, plus 2, which is 11 ohms. Okay, so my current, to rearrange this, is going to be V divided by R, which is going to be 10 volts, divided by 11 ohms, and I need my calculator, okay, and 10 divided by 11 is 0.909, so I'm going to go with 0.91 amperes of current, okay? And it winds up being in amperes. Just kind of trust me on that. We're going fast, all right? But that's what it winds up being. So that's how I solved for the current. Now I'll do another one. I'll do it in parallel, okay? So let me erase this. All right, so let's say we'll go with 10 volts again. Whoops. 10 volts. And let's say that, okay, so I have a 3 ohm resistor, and then I have a 2 ohm, and that's in parallel with a 3 ohm resistor, and that's it. Okay? Now, how much current, what's the total current I going through this circuit? Okay? All right, so V is equal to I times R. Now again, the question is, what is the total R? Okay, well, here's a 3, and that's hooked up. Now these two, now listen, these two, the 2 and the 3 over here are in parallel. But together they look like one resistance that's in series with the 3 up here. So what I'm going to do is I'm going to add these two here the parallel way to get one number, and then I'm going to add it to the 3. So what is the equivalent resistance of this 2 and 3 together? Well, it's 1 over, I'm going to call it R23, for example, for the 2 and the 3, is equal to 1 over 2 ohms plus 1 over 3 ohms. So that's 0.5 plus 1 over 3 is 0.33, which is 0.83. Now, R23 is the reciprocal of 0.83, okay? And again, that's getting a bit of a glare on there. I'm sorry for that, okay? All right, let me see if I can do this. Nope, not helping that much. Okay, all right. But anyway, so that's 0.83, 1 over 0.83. 1 divided by 0.83 is, whoops, I did it wrong. 1 divided by 0.83 is 1.2. Yeah, 1.2. 1.2 ohms. Okay, so my equivalent resistance here, this is the same as a 1.2 ohm resistor. Notice that 1.2 is less than the 2. Remember, it's less than your smallest resistance. Okay? All right, so my total resistance in the circuit, so this is like one 1.2 ohm resistor. So what's my total resistance in the circuit? Well, my total resistance, RT, is equal to 3, okay, ohms plus 1.2, which is 4.2 ohms of resistance totally. Remember, to the current, it looks like this is one big, this array here looks like it's just one 4.2 ohm resistor in the circuit, okay? So what is my current? Well, I is equal to V divided by R. So that's going to be 10 divided by 4.2, 10 volts divided by 4.2 ohms. And I'm going to divide 10 by 4.2. Okay, so 10 divided by 4.2 is 2.3 amperes, okay, of current is what I'm getting. I'm writing it where there's not a glare. Okay, I'm going to come up with some problems for you. Well, actually, I'm posting some problems for you guys to solve, some Ohm's Law problems. All right, and all right, so I would expect that you're going to have some questions on these. So again, see me during the office hours. All right. And I'll be around. So remember, take good notes on this. See me during the office hours. Try the problems and enjoy your apocalypse. Goal us out.